Hello. In this lecture we will talk about authentication header. So far we talked about the IPsec protocol, the IPsec. There are two main protocols: authentication header and encapsulation security payload. Authentication header doesn't do encryption. Authentication header only provides data integrity but does not provide data confidentiality, which is encrypting the data. Authentication header uses anti-replay to make sure that packets don't get captured and resent or replayed back by an attacker. With anti-replay detection, the sequence number cannot repeat again. If we look at the actual authentication header, it starts by the next header, which is the actual protocol that is carried inside the payload. This points at the IP protocol number, whether it's TCP, UDP or ICMP, and so on. The payload length is the length of the authentication data field in 32-bit words. The name is misleading. It doesn't mean the actual payload in the packet, it is the size of the authentication data. The authentication data is the integrity algorithm output or the integrity check value, ICV. For example, if SHA-1 is used, this would be a 96 bits output. The AH header also contains a security parameter index. It follows the same concept we discussed previously, with phase 2 providing this number. To combat replay attempt, sequence number is used. Each packet that goes back and forth between the initiator and responder has a sequence number. The sequence increments for each packet sent. The sender and receiver counter are set to 0 when a new SA is established. If anti-replay is enabled, which is the default, the sequence number is never allowed to repeat. The sequence number is a 32-bit number, so the maximum number of packets is 2 to the power of 32. This is around 4 billion packets. After 4 billion packets are exhausted, the session must renegotiate a new SA to start a new counter. For a very busy network, this number is pretty small. So, to expand this and avoid renegotiation of the connection frequently, the extended sequence number is used. This extended sequence number increases the size to accommodate for high-speed connections. This would extend the sequence number bit size from 32 bits to 64 bits. The 32 bits in the header are the low-order bits and the 32 bits field extension in the header are the high-order bits. And then after that, you can have the integrity check value. So the integrity check value is the outcome of the integrity operation. The system will run the payload of the packet through the hashing function and come up with the integrity check value. And that will be what's going to be added to the packet. The size of the ICV depends on the algorithm. So, this is of a variable length. The AH header must end at a 32-bit boundary. To comply with this boundary, if the ICV length causes the header to not end at a 32-bit boundary, ICV paddings are added. The payload length that we discussed indicates the size of the ICV. So, the ICV is the one that provides integrity. The senders computes the value against the payload and it includes this ICV value in the header. The receivers would run the same operation on the received packet and compares its own calculation of the ICV output against the ICV in the AH header. If the two matches, the packet integrity was proven. If they don't match, the receiver will discard the packet. So there's two types of IPsec encapsulation, which is tunnel mode or transport mode. In transport mode, the sender inserts the authentication header after the IP header and before the next layer protocol header. This is the original packet before applying the authentication header. The original IP address would basically move forward with the options and everything. And then the system inserts the AH header followed by the original payload, which could be TCP or UDP, etc. So the original IP header get copied into the new packet. The ICV is calculated based on the immutable fields in the packet, the fields that don't change. For example, TTL changes at each hop, this field is excluded. The ICV is added to the AH header following by padding and then the original data payload that was in the original packet. So, in transport mode, the only benefit from an authentication header perspective is that the integrity and anti-replay features are implemented. The traffic in AH transport mode, the original IP source destination doesn't change. In tunnel mode, the actual source and destination of the authentication header packets are going to be changed. They will be the IP address of the IC gateways. So the original packet is encapsulated inside a new packet with a new IP header that has the source and destination of the IPsec gateways. The integrity is calculated based on the entire packet excluding mutable fields. Let's move on to encapsulation security payload. Encapsulation security payload provides confidentiality and integrity. The integrity uses the anti-replay that we talked about. It's the same concept that we talked about in the authentication header as for the encapsulation security payload. The actual ESP header looks like this. You first start with the security parameter index. And then you have the sequence number that basically would increment each communication. Each time the two IC gateways talk to each other. And then you have the payload data, which is the actual payload that was encrypted. So basically, it does the encryption and put the outcome inside the payload data. And then you have some padding which is done to obfuscate the data and then also to align the bits with the algorithm that's used at the algorithm bit boundary. And then you have the integrity check value at the end. The sequence number is in clear text, but everything after that is encrypted. If somebody is sniffing the traffic between the source and destination IC gateways, they will only see the security parameter index and then sequence number. Then everything below that will be encrypted. Also, the same thing with the authentication header transport mode or tunnel mode. Same thing with ESP, you have the transport mode or tunnel mode. The transport mode basically uses the original IP address information, source and destination, and then attaches the ESP header and everything at that point is encrypted. And at the end you have the ICV, which basically is the integrity. This is in transport mode. And in tunnel mode, the IP addresses changes to the IP address of the source and destination gateways. And the original packet is actually the payload that gets encrypted and sent on to the other side. So the difference between transport mode and tunnel mode is, transport mode does not hide the original source and destination, while tunnel mode hides the original source and destination. We will discuss more in the next lecture.